Multivariable calculus, we are in section 14.6. So sorry that we couldn't finish that last problem. I'd like to do so now in the remaining video. We found the vector PQ. We even found the length of vector PQ. And the reason why, guys, is as we are taking a derivative in a particular direction, we're going to use a vector, but it must be a unit vector. And so I'm going to write over here, we've got unit vector, and that plain and simply will be the vector PQ divided by the length of PQ. And that's something that we did quite a bit of in chapter 12. So we saw up above that vector PQ is -3/2, comma 2. And we know from, even as we were talking in the previous video, that that length surely is not 1. In fact, we just found the length. It's actually 5/2. So I'm going to divide both of these components by 5/2. That's essentially what's happening. And that means that our unit vector, well, here you can see that your 2's would cancel out. You could see you'd be left with a -3/5. And, with the 2 divided by 5/2, well, that's like 2 times 2/5, which would be 4/5. And we always need to do that. That's, really such an important step in finding a directional derivative in a vector's direction. You must work with a unit vector. And, as we've been talking earlier in the notes, that could be designated as A and B. So as we're answering part A right now, try to find the rate of change of f, find that derivative in this direction. Well, we can write this in this style, du prime of f of x comma y. Well, what is that? That's f sub x, the derivative of f with respect to x, times a, plus f sub y, the derivative of f with respect to y, plugging in a b. And we already found f sub x, that was e to the y, right? And our a, well, we did that down here, that's -3/5. And f sub y, well, this is a little bit more work. It's your x e to the y. But then, of course, our b, our b was down at the bottom here. That's 4/5. But, of course, what is happening? I'm going to draw this vertical bar here. This is at the point 2, 0. In other words, wherever we have an x, plug in a 2. Wherever we have a y, plug in a 0. And what will we get? Well, I think you can see pretty quickly, we are going to get an e to that 0. We'll have times -3/5. And then we'll say plus, well, then we'll have a 2 times e to that 0 times 4/5, and then we just have to do a little bit of cleaning up. So you can see e to the 0, of course, is just a 1. So we will be left with -3/5. And here's 2 times 4/5. Well, that's 8/5. And, that's 5/5, which is just a 1. So what are we really seeing? That derivative at the point 2, 0 is going to be a 1. So, wow, that's really what we've got. For part B, they're asking something very different. In what direction does f have the maximum rate of change? And what is this maximum rate of change? Well, as we just saw up above in this theorem, we saw that really the maximum value of this directional derivative is the length of that gradient, of delta f of x right there. And it occurs when u has the same direction as that gradient vector. So let's just review real quickly. We've got the gradient of f is, of course, as we saw, it was f sub x, f sub y, and we already did that. And of course, we could say, well, plug in that 0.20. We already did that earlier, right here with the 1 and the 2. You can see pretty much where we're going with that. So what I can now say is f has the maximum rate of change. It's that maximum rate of change in the direction of 1, 2. Okay? But there's a second part. There's what is this maximum rate of change? Well, the maximum rate of change was the length of the gradient. And, just taking the length of that vector, well, we can say it's 1 squared plus 2 squared. Well, that's 1 plus 4. That's radical 5. And this is the maximum rate of change. So, sorry we couldn't squeeze that in. I will get this video posted. Hope this is making sense.